some problems with the heavy rain today. I'm very happy to introduce the first speaker of the morning, who is Professor Eduardo Garcia-Rio from the University of Santiago de Compostela, Spain, and the title of his talk is Osserman Manifolds.
Thank you. So thank you very much to the organizers for the invitation. It's a big pleasure to be here back in Rio once more, and mainly on the occasion of celebrating the 60th birthday of Marcos. So, feliz cumpleaños, que cumplas muchos más. So I should say that my work has nothing to do with submanifold theory, and the relation with the previous work of Marcos goes back to maybe his first paper, which was in the early 80s. It was jointly with Nomizu. He studied some properties of the curvature of pseudo-Riemannian metrics. So first of all, I would like to introduce the topic we are going to talk today. So the general idea behind all this work is to understand the geometry behind some special algebraic properties of curvature operators. So for the whole of this lecture, I will denote by Mg a pseudo-Riemannian manifold. So sometimes this metric will be positive definite, sometimes will be Lorentzian, and sometimes will be of arbitrary signature. Nabla stands for the Levi-Civita connection, and R is the curvature tensor. We use this sign convention, but this is not so important. So associated with the curvature tensor, there are a large number of operators one can construct, but probably the most well-known operator and the most widely studied is the Jacobi operator, which is defined as follows. For each tangent, for each vector, we are assuming at this moment that this is a space-like or time-like unit vector. We take the curvature operator, and we fix these two entries by x. So this is the usual Jacobi operator when one studies geodesic deviation. And this operator is self-adjoint due to curvature identities. So one may look at the spectrum, and the spectrum of this operator naturally depends both on the choice of the direction x and the base point we are on the manifold. So if these eigenvalues are assumed to be independent both of the base point and the direction, we say that the manifold is Osserman. So this means, in other words, that the eigenvalues of the Jacobi operators are constant on the unit sphere bundles. So first, trivial examples of Osserman manifolds are isotropic manifolds. So if the group of local isometries acts transitively on the unitangent sphere bundle, then clearly the eigenvalues of the Jacobi operators are constant. So for instance, if you think on a Riemannian geometry and you take any of the two-point homogeneous spaces, all of them are Osserman. And the initial conjecture on this topic was due to Osserman, who stated that those were the only possible examples in the Riemannian case. So the purpose of this lecture is, firstly, I will review what is known in the Riemannian case, where the Osserman conjecture is almost completely solved. Then I will consider the case of Lorentzian metrics, and in that case, one has a very simple answer, which is rather easy to show. And then we will go back to other signatures, in particular to signature 2,2, and I will especially emphasize the situation in dimension 4, which is quite illustrative of the general situation. So at this moment, we are assuming that our metric is positive definite. So when one wants to understand the Osserman problem, the solution usually has a two-step process. So firstly, one has to solve a kind of algebraic problem, which consists on determining all the algebraic curvature models. So it means all the algebraic curvature tensors which are Osserman. So this is a question as a fixed point, and it's purely algebraic. And then one has to decide which of these algebraic solutions may be realized at the differentiable level. So you have the Osserman manifolds. So if you want now to construct examples of algebraic curvature tensors which are Osserman, I will show you how to construct a large family of them. So what you have to do, you take a Clifford model structure. So for a moment, this is nothing but you take a set of complex structures which anti-commute and are orthogonal on the vector space. So there are some topological restrictions of the existence of this structure, but for a given structure, one can construct an algebraic curvature model with any given eigenvalues. So if you look at this expression here, this part of the curvature is nothing but the curvature of a real space form, space of constant sectional curvature, and this part here, when you take one of the complex structure, if you plug these together, gives you the curvature of a complex space form. So somehow you have large number of complex structures and you are deforming the curvature in those directions. So for any set of constants, lambda 0, lambda mu, you may construct an algebraic curvature tensor which is Osserman, and where the eigenvalues are exactly lambda 0, lambda mu for the Jacobi operators. So you have a large number of solutions at the algebraic level, and the problem is to decide whether this can be realized at the differentiable level. So the first question is whether these solutions are the only possible solutions. So in showing that, what one usually uses are techniques from algebraic topology, and I will try to show you how to handle the easiest case when one has the dimension of the manifold is odd. So in that situation, if you have a 2n plus 1 dimensional manifold, and if you take now this at each single point, you consider the tangent space, and you take the unit vectors. So what you take is the unit sphere. So for each unit vector x, the Jacobi operator is an endomorphism of the normal space, which is nothing but the tangent space to the sphere at this point x. So if you have an eigenvalue lambda for the Jacobi operator with a multiplicity m, you may use this eigenvalue to define a distribution on the sphere. So you may define d lambda to each point on the sphere sets to the corresponding eigenspace. So this, since manifold is Osserman, this distribution has constant dimension m. And now what indeed Chi did in the 80s is that since we are now in an even dimensional sphere, we know that there exists no plane fields other than the 0, 1, and the total space. So this means that this multiplicity m has to be equal to 2m. So this proves that there may be only one eigenvalue for the Jacobi operator, and hence all Jacobi operators are multiple of the identity. So in this case, all you have is that the curvature tensor reduces to this part here. This is just some algebraic manipulations. And using that, he was able to show that in that dimension, the curvature you have is that one corresponding to a Clifford zero structure, so you have no Clifford structure, and the solution has to be a real space form. Quite similar argument, but slightly more complicated, can be used to solve the case of dimension 4m plus 2, which also was handled by Chi. And in that case, you may have two possibilities when you consider these plane fields on the sphere, that either is the total space or it's one-dimensional. So it means that there exists a distinguished eigenvalue of the Jacobi operator, which is one-dimensional, and you may use it to construct an almost complex structure, which after some work, one can show that it has to be indeed a Keller structure of constant holomorphizational curvature. So since the work of Chi in the 89, what remains open is the case of dimension for n, which was recently solved by Nikolajewski, who proved that in any dimension for n different from 16, you have a quaternionic Keller structure of constant quaternionic sectional curvature. So the whole problem is completely solved, but as far as the dimension is different from 16. And the reason for that is that in dimension 16 is where you have the Cayley plane, and due to the lack of associativity of the octonions, the curvature tensor of the Cayley plane cannot be expressed in terms of a Clifford model structure. So this is the real problem to understand this remaining case. And essentially, this is the whole picture in the Riemannian setting. If you now turn to the Lorentzian case, the situation is a little bit different, because in this case, we have space-like, time-like, and null directions, and space-like and time-like sphere bundles are disconnected. So one may study separately the condition to be space-like and time-like Osserman, and since every null vector can be approached by a sequence of space-like or time-like vectors, you may also consider the null Osserman condition. And in that case, the Jacobi operator has to be nilpotent, because if it is space-like Osserman or time-like Osserman, if you approach a null direction, then the eigenvalues has to vanish. So the first result in this direction is that in this setting, all these conditions are indeed equivalent. So a manifold is space-like Osserman, if and only if it is time-like Osserman. This is rather general for any arbitrary signature. And in the Lorentzian case, this is also equivalent to be null Osserman. So here is important to emphasize the fact that even though they are eigenvalues of the Jacobi operators are constant, they may be different from space-like to time-like directions. And so if we want to consider now these manifolds, and we want to solve firstly the problem at the algebraic level, the first thing is that one cannot use these techniques from the analogous techniques as in the Riemannian case, because when we think on the pseudosphere, this is non-compact. So this kind of algebraic topology abstractions are not working well in this setting, but still one can solve the problem, and surprisingly, the solution is extremely easy in this case. So the only algebraic Osserman algebraic curvature models are those of constant sectional curvature in the Lorentzian setting. And the reason for that is that if you assume that a manifold is Osserman, and if you choose a time-like direction, then eigenvalues of the Jacobi operators are constant, and you can bound all the sectional curvatures corresponding to planes of signature plus minus. And this is one of the big differences when one considers or studies the curvature of pseudo-Riemannian metrics in comparison with the case of the positive definite metrics, that the sectional curvature is not defined on the whole Grassmannian of two planes, since one has to exclude the degenerate planes. So since the definition of the sectional curvature is an open set, this sectional curvature is not necessarily bounded, and it is bounded if and only if the sectional curvature is constant. So in this case, the solution is easy. We have only one family of algebraic curvature models, and all of them can be realized at the differentiable level. So in this case, we have that the solution at the algebraic problem is equivalent to the solution at the differentiable problem, and is also equivalent to the, I call a pointwise problem. I'm not to say more about this pointwise problem, but this essentially is the condition that when you have a manifold where all the Jacobi operators have constant eigenvalues at each point, but those eigenvalues may be changed from point to point. But in this case, the sure lemma says that all these conditions are equivalent. So if we now turn to the case of other signatures, the case we are going to consider now is that of neutral signature 2,2. And so the firstly, two words just to why we focus on this dimension 4. And the reason for that is that any Osserman manifold is Einstein, And this is just due to the, you can just construct the Ricci tensor by tracing the Jacobi operators. So if the eigenvalues of the Jacobi operators are constant, then your manifold has to be Einstein. And then in dimensions 2 and 3, you have a necessarily constant sessional curvature. So this means that dimension 4 is the first non-trivial case for consideration. So in this case, when we consider the Jacobi operators, well, we may think on the Jacobi operators are endomorphisms of the tangent bundle, but due to the curvature identities, we may restrict those endomorphisms to the normal space of the direction x. And in this case of neutral signature, all this normal space has induced a Lorentzian signature, either of signature minus minus plus or signature minus plus plus. But in each of these cases, this is a self-adjoint operator, and then we have 4 different possible Jordan normal forms for this operator. So it may be either diagonalizable, or it may have a complex eigenvalue, may have a double root of the minimal polynomial, or may have a triple root of the minimal polynomial. So I will keep this the notation of type 1a, 1b, 2, and 3 in the next slides. So these are the possibilities for the Jacobi operator. So the first question is whether these possibilities are realized algebraically. So, and in order to show that, what we have to do, we consider a Clifford 1-1 structure. So this is some kind of neutral signature analog of the what is a quaternionic hypercomplex structure. So what we have is that we have a complex structure, and we have 2 product structures with eigenspaces of equal dimensions. So this is what's called a paracomplex structures, and they anti-commute, and they are, all of them are skew symmetric with respect to the metric. And in this case, one of the important facts of these families is that when you have a hypercomplex structure and you take combinations, you always obtain new complex structures after scaling. But in this case, you may obtain 2-step nilpotent operators, which are skew symmetric, and you may obtain also product structures, which are still skew symmetric. And each of them give rise to curvature algebraic tensors, and then one may easily construct an algebraic curvature tensor of this form. If you remember from the Riemannian case, in the Riemannian case, what we have is something like this, where R0 is the curvature tensor of a real space form, and R phi A is the curvature tensor corresponding to those terms corresponding to the complex structures. But in this case, you may also have these nilpotent parts here, and if one plays a little bit with all the constants lambda 0, lambda I, lambda ij, one can show that in this case, all the possibilities for the Jacobi operators are realized at the algebraic level. So we have to consider indeed all these cases. And so the question is whether these algebraic possibilities can be realized at the differentiable level. So this is the next step. So in order to do that, we need a criteria for a manifold to be Osserman. And here is where this pointwise Osserman condition comes again, that at the algebraic level, all these algebraic curvature tensor can be characterized by the property of being self-dual or anti-self-dual. It depends on the choice of the orientation, and all of them are Einstein. So we will strongly use this characterization in what remains. And another further observation is that when you decompose the curvature tensor acting on the space of 2 forms, you have this term coming from the scalar curvature, the trace-free part of the Ricci tensor, and then you have the self-dual and anti-self-dual Weil curvature operators. But the difference with the Riemannian case is that in the case of neutral signature, the induced metric on the space of self-dual and anti-self-dual 2 forms has a signature of Lorentzian signature plus minus minus. So this is the main difference. So what's happening in the case of the Jacobi operators are diagonalizable. So first of all, I will come back again also to the Riemannian case, because this is somehow we can handle together the Riemannian and the pseudo-Riemannian cases here. And when you think on this approach by Chi, everything relies on the fact that the sun spheres do not admit plane fields. And indeed, all these things work pretty well, but there are some very exceptional cases where you cannot say anything about the structure of the eigenvalues. And these are the cases when the dimension of the sphere is 3 or 7, because in these cases these are parallelizable. So this corresponds to dimension of M equal to 4, and this corresponds to dimension of M equal to 8. So in these two cases, even in the Riemannian setting, the proof, which is result is true, but the proof is not so simple as for the other cases. So I will try to give you an idea of how you can get the description of all these manifolds, both in the Riemannian and in the neutral signature cases. And first of all, say that the solution is due to work of Blasik, Bokan, and Rakic. And the solutions has real space forms and complex space forms. You already know these spaces. They are the indefinite versions of the Riemannian cases, but there is also another family, which is the paracomplex space forms. So just for fixing the notation, since we are coming back to this family later on, what a paracomplex space form is a parakeller manifold is just a symplectic manifold which is locally diffeomorphic to a product of Lagrangian submanifolds. So what we have is a manifold M, and we have a two-form which is closed, and moreover we have a decomposition of the tangent bundle as a sum of Lagrangian submanifolds. So we can construct the 1-1 tensor field, which is given by the projections on these Lagrangian submanifolds, and since these L and L prime are Lagrangians, one can immediately check that this is Q with respect to the symplectic form. So one can use the symplectic form to define a metric G, and this metric G turns to be of signature NN. So manifold is of signature to N here. And now you can express the fact that the form omega, two-form omega, is closed, and that these two bundles are integrable equivalently by saying that the covariant derivative of this paracomplex structure is parallel. So it's a quite analog of the Keller situation. And you may use this paracomplex structure to define what is called the paraholomorphizational curvature. So a paracomplex space form is just a parakeller manifold of constant paraholomorphizational curvature. So this is somehow you may think on this as a kind of a real version of the Keller structures. So how you can prove these things? So what we have to do, this is not the way they prove originally, but I think is you can also see which is the difference between these complex and paracomplex space forms. So you use that the Osserman manifolds are characterized as those self-dual and Einstein manifolds. So in that case, the curvature operator reduces to this part. So there is no trace-free part of the Ricci tensor, since this is Einstein, and this anti-self-dual part is also 0. So what you have to do is to consider the different possibilities for this self-dual Weil operator, and the crucial fact is that there is a 1-1 correspondence between the Jordan normal form of the Jacobi operators and the Jordan normal form of these self-dual or anti-self-dual operators. Eigenvalues are not the same, because, for instance, this is a trace-free, but the Jordan normal forms have to be the same. So what you have to do is to consider the different possibilities. So if W plus has 3 equal eigenvalues, then it has to be 0. And in that case, if you have a 0 here, you are in a space of constant curvature, since locally conformally flat and Einstein, sectional curvature is constant. The case where you have 3 distinct eigenvalues is excluded, and the reason for that, essentially, I will not spend much time on this, but is that associated to each distinct eigenvalue, you can construct a complex or paracomplex structure. And since the eigenvalues of this operator are constant, because the eigenvalues of the Jacobi operator are constant, you can use that the bundle of self-dual forms is parallel to show that you should have a hyperkeller structure which should be Ricci flat, and then you have a contradiction. So the remaining case and the interested case is where this self-dual curvature operator has exactly two distinct eigenvalues. And the best way to conclude is to use what's called the generalized Goldberg-Sachs theorem. So this is a result by Derzynsky in '83. So it was almost 6 years before the result of Chi, that you have an Einstein manifold with degenerate self-dual bicurvature operator. So this means that the number of distinct eigenvalues of the self-dual curvature operator is 1 or 2. Then there exists a Hermitian metric which is locally conformally Keller in an open dense set. And the conformal factor is given by the norm of the self-dual curvature operator. So the idea is that as soon as you have two distinct eigenvalues, one of them must have multiplicity 1. So you can take an eigenvector, which is a two-form, self-dual two-form. So at least locally, this self-dual two-form gives rise to an almost Hermitian structure. And using the fact that the metric is Einstein, one can show the integrability of that structure. Now, what we can do, how can we use this result to solve the Osserman problem is that since if we assume that the manifold is Osserman, then the eigenvalues of this self-dual curvature operator has to be constant. So the norm has also to be constant, and hence this conformal factor is indeed a scalar. So what we are saying is that then the metric is not only Hermitian but Keller, and since it is self-dual, this anti-self-dual curvature operator vanishes, and this is equivalent to the vanishing of the Wagner tensor. So the Wagner tensor, you may think on it as a kind of complex version of the Weil tensor, but the important thing for us is that any Einstein-Keller metric with vanishing Wagner tensor has to be necessarily a complex space form. So this is the way you can conclude. So when you now pass from the Riemannian case to the pseudo-Riemannian cases, you have to consider two different situations when this distinguished eigenspace is space-like or time-like. In the case the distinguished eigenspace is time-like, it gives rise to a para-Keller structure, while in the case it is space-like, gives you a Keller structure. Well, one has to be careful that in the case of the Keller structures in signature 2-2, the complex structure and the Keller form induce opposite orientations on the manifold. So one has to replace self-duality by anti-self-duality in this situation. But in all the cases, one works exactly in the same way as for the Riemannian case, and one can show that this gives rise to a complex space form or to a paracomplex space form. And also an important thing is that in all these cases, the diagonalizability of the self-dual curvature operator is an essential ingredient of the proof. So these pseudo-Riemannian extensions are no longer true if you remove that condition. But since we are assuming the Jacobi operators are diagonalizable, then so is the self-dual curvature operator, and we have no problems at this stage. So the next case to be considered is the case of complex eigenvalue. And the situation here is that this algebraic possibility cannot occur at the differentiable level. And this was fairly shown by Blasik, Bokan, and Rakic by some direct calculations, but one can give somehow more clear proof of that, which is the following. Since we know that there is a one-one correspondence between these Jordan normal forms, what we know is that any Osserman metric in dimension 4 having a complex eigenvalue is zero curvature homogeneous. So this means that for each point, for each pair of points, you have a linear isometry which preserves the curvature tensor. But since the manifold is Einstein, Derzynsky showed in 2003 that all these manifolds has to be locally homogeneous, and moreover, he proved that when you consider the curvature operator acting on the space of two forms, it has eigenvalues lambda and lambda to e to the 2 pi I over 3, and this other eigenvalue. And these eigenvalues are exactly the same for the action on the self-dual forms and for the action on the anti-self-dual forms. So this means that the manifold, a manifold like this, cannot be anti-self-dual and having, because in that case, all these eigenvalues has to be 0. So the solution is that you may have not such kind of Osserman metrics. Okay, so what's happening with the case 2, type 2, when you have a double root of the minimal polynomial of the Jacobi operators? So in this case, we have the algebraic level. We know that this possibility may occur for any pair of eigenvalues alpha and beta. However, if we impose that this has to be realized at the differentiable level, we have a big restriction. So these eigenvalues either vanish or they are in a ratio 1 over 4, which is the ratio we also have for the Keller geometry, for the quaternionic geometry, and for the Cayley plane. In the first case, the Jacobi operators are two-step nilpotent, but in the second case, which is the one we are more interested in, what we have is a Walker metric. The underlying metric has to be Walker. This means that the metric admits a parallel degenerate plane field. So this is a purely pseudo-Riemannian situation. When you work in the Riemannian geometry, and if you have a plane field which is parallel, the orthogonal plane field is also parallel, and your manifold locally decomposes as a product. This is the local Durand decomposition. But in the pseudo-Riemannian setting, the same is true if you are, as long as the restriction of the metric to your planes is non-degenerate. But if the restriction of the metric to this plane is degenerate, it gives no rise to a local decomposition. And this is what is called a Walker metric. And just for maybe 2 minutes, I will try to do some publicity about these metrics. And the reason for that is that usually when one works in pseudo-Riemannian geometry, one may try to generalize results from the Riemannian case to the pseudo-Riemannian case. And in most cases, this can be done with a little bit of work. But if you really want to understand the difference between the Riemannian and the pseudo-Riemannian situation, certainly you have to pay attention to these metrics. And I want to show you just a very few list of examples where you have some pseudo-Riemannian properties that they may never occur in the Riemannian case, where the underlying geometry is that of a Walker metric. So if you are interested in a holonomy, if the holonomy acts reducibly on the manifold, it means that it lives invariant. There is a subspace which is invariant under the action of the holonomy, but this space is degenerate, and there is no other invariant subspace which is non-degenerate. So this is a purely pseudo-Riemannian situation, and in that case, the metric you have is just a Walker metric. If you are interested in studying conformally equivalent Einstein metrics, then the local structure of those metrics depends on the gradient of the scaling function, and whether this gradient is non-null. The situation works quite the same in both cases, but in the pseudo-Riemannian case, you may have a conformal deformation where the gradient of the scaling function is a null vector at each point, and in that case, you also have a Walker structure. The same occurs when you study some curvature properties like being conformally symmetric. Conformally symmetric means that the Weyl tensor is parallel. So in the Riemannian setting, manifold with parallel Weyl tensor is either locally conformally flat or locally symmetric. There are no other possibilities, but there are some possibilities, two possibilities in the pseudo-Riemannian case, which all of them come from Walker structures. If you are interested in studying Einstein hypersurfaces in space forms, you have some possibilities for the shape operators, and Magid proved in the in the 80s that in that case, if the shape operator is nilpotent, what you have is indeed a Walker metric on the hypersurface. And also the same is true for these para-Keller structures. Indeed, the situation is that if you think on this paracomplex structure, which is parallel, this has no complex eigenvalues, but real eigenvalues plus 1 and minus 1, which corresponds to the distributions L and L prime, and both distributions are degenerate for this metric. But since the paracomplex structure is parallel, these two subspaces are parallel. So this is even a very special case of Walker metric when you have two complementary distributions which are parallel. And the case of hypersymplectic structures is also, in that case, you also have a parakeller structure, so it's necessarily a Walker metric. Well, just for doing some more publicity, if you are interested on Walker metric, there is a monograph, it just appeared 1 month ago, but it is available at those strange places where you can find PDFs of everything already 3 months ago or something like that. Okay, so come back to the Osserman problem. So what we are interested now is in the understanding this family of metrics. And the important thing for us is that Walker showed the existence of adapted coordinates in this situation where the metric can be expressed by 3 different functions. So this reduces the number of unknowns very dramatically and makes things quite easy to understand. So another important observation is that once you have a Walker metric, if you have a degenerate plane field, it orients the manifold itself. So we have to, there is a natural distinction between self-dual and anti-self-dual Walker metrics, and they are completely different. So just let me show you some easy examples, and which at the end they turn out to be really important in our analysis. So the first of them goes back to the 50s by Patterson and Walker, and they call it a Riemann extension. So the situation is that if you take a torsion-free connection on a manifold, we will consider the 4-dimensional case. So for our situation, most of the times this will be a surface. If we take a torsion-free connection, then we can define a metric on the cotangent bundle, which is given in local coordinates by this expression, where gamma, I, J, K are the Christoffel symbol of the connection. What this essentially does is that you can determine this metric by its action on complete lifts of vector fields on the base, and what you do is that this metric acts by evaluating the symmetrization of the connection here. So after this is I give here the expression in coordinates, but this is a globally defined metric, no problem for that. So in this case, this is a Walker metric where the vertical distribution of the bundle is parallel and degenerate. And one can modify this a little bit, and this is the real important case for us. If we take an arbitrary symmetric 0 to tensor field on the base, we can pull it back by the projection to the cotangent bundle, and this gives to some modification of the Riemann extension. We call it the form Riemann extension. This matrix has been characterized by Afifi as those the only Walker matrix whether you have this property for the curvature. So in particular, this means that when you take the Jacobi operators corresponding to planes tangent to the vertical distributions, they always vanish. And these metrics have been useful, very useful in understanding some questions in affine geometry. And the reason for that is that you may relate properties of this torsion-free connection, affine properties with pseudo-Riemannian properties of the Riemann extension. And sometimes it's much easier to solve the problems upstairs and then take the solutions and study the things at the affine level. Well, for our purposes, there is also another modification of these Riemann extensions that we introduced just this year. So what we do is that we take the form Riemann extension and we add another term here, which comes from an arbitrary 1-1 tensor field on the base manifold. So what we do is that if this is a 1-1 tensor field, iota here means the evaluation map. This is one form of the cotangent bundle, so this is adding a symmetric part to this. And also in this case, you have a Walker metric where the parallel distribution is again given by the vertical subspace of the bundle. So if you express in local coordinates, you have something like that. But I mean, this is not important at this moment. So this modifier Riemann extension has some really nice properties. The first of them is that it produces an infinite family of Einstein metrics on the cotangent bundle. So indeed, if you take this special situation, here you choose the 1-1 tensor field to be the identity, so no problems with that, and you take an arbitrary connection on the base manifold of any dimension, and you then choose this 0-2 symmetric tensor field to be, after some scaling, the symmetric part of the Ricci tensor of the connection. So in the affine geometry, if you take the Ricci tensor, needs not to be symmetric as in the Riemannian or pseudo-Riemannian geometry, may have also an skew-symmetric part. So you have to forget about the skew-symmetric part, and this construction gives new Einstein metrics on any dimension. And these metrics are not Ricci flat. Here, all of them have constant scalar curvature 1. You may get the scalar curvature 1 just plugging here some constants. And as a special, very special case, one can use these modifier Riemann extensions to describe locally paracomplex space forms. So the paracomplex space forms locally are modifier Riemann extensions of, indeed, a very special class of connections. So you have to take a flat connection, then this part here disappears, and this gives you a local description of a paracomplex space form of paraholomorphizational curvature C. And the other important thing for us is that in the special case when the base manifold is 2, so we have a fine surface, we can use this a version of these modified Riemann extensions to describe all the self-dual Walker metrics. So, and the result is that any self-dual Walker metric is locally the cotangent bundle over a surface, where in this case what we have is as a kind of modified Riemann extension, where here we have to use the identity and some 1-1 tensor field and 1 vector field. So if you think from that point of view, all self-dual Walker metrics are parameterized by an affine connection, a vector field, and 1-1 tensor field, and a symmetric 0-2 tensor field. So since we are interested in the case of Osserman metrics, we are interested in those Walker metrics which are self-dual and Einstein. So if they are self-dual, they are locally this kind of modifications of the Riemann extensions, and then we can use the Einstein condition here to give the result. So the result is the following. We already knew that if the eigenvalues are in this non-zero, then the metric has to be a Walker one. And in this case, we have two possibilities. It may be self-dual or anti-self-dual. We were very, very lucky because in this case of the anti-self-duality implies Ricci flatness. So this matrix cannot be anti-self-dual. So this skips the worst part of the problem because we do not know really how to deal with this anti-self-dual Walker matrix. So it has to be necessarily self-dual, and in that case, this is the complete solution. So any Osserman metric with these eigenvalues and this kind of Jacobi operator is locally the modified Riemann extension of an arbitrary torsion-free connection where this pullback is just the trace symmetry part of the Ricci tensor. So this means that for any connection you choose, you have in the cotangent bundle one of these metrics. And this was rather surprising because for a long time we knew the existence of samples where the Jacobi operators were two-step nilpotent. And even it was conjectured by Gilkey and Nikolajewski that these metrics may not exist at the differentiable level. And finally, it turns out that they not only exist, but there is a huge number of them. So for any connection you plug here, you may have one of these metrics. So what can you say for the other case? In the other case, we only have partial results, and this is mainly due to the fact that in this case metrics may be Walker self-dual or anti-self-dual. And really, if you look at the anti-self-dual part of the curvature tensor, that is horrible and somehow it's hopeless to expect to have a result like the previous one. So what we know is that only for the case of the self-dual metrics, that all these metrics with alpha equal to beta equal to 0 are deformed Riemann extensions, where in this case this is an arbitrary 0 to tensor field, but the connection is necessarily flat. So it essentially depends on this symmetric 0 to tensor field. So what can we say about the other case when the Jacobi operators have a triple root of the minimal polynomial? So in this case, we have clearly two possibilities, whether these Jacobi operators are three-step nilpotent or whether this eigenvalue is different from 0. In the first case, Derzynsky recently showed that all these metrics has to be Ricci flat and self-dual. So we are very lucky that in that case, we can give a complete description of them, and what we obtain is that all of them are deformed Riemann extensions, where when you think in the previous case when we have two-step nilpotent operators, we have an arbitrary tensor field here and a flat connection here. In this case, what we have is a connection with skew-symmetric Ricci tensor. Remember, the Ricci tensor may be symmetric or not, so it has to be strictly skew-symmetric, and we have an arbitrary tensor field here. So the fact that the Ricci tensor is skew-symmetric in dimension 2 defines a volume form of the manifold. So if you take the covariant derivative of the Ricci tensor, it has to be a multiple of itself. So in particular, this shows that all manifolds, all surfaces with skew-symmetric Ricci tensor must have recurrent curvature tensor. And once again, we are very lucky because due to some work of Wong and Derzynsky, we can give the complete solution to this case. And there are essentially only one connection corresponding to this situation, which is given in some suitable coordinates by this expression where theta is an arbitrary function of the two variables. And this connection is just to ensure that the connection is not flat. So in this case, what we have is just essentially only one connection, which is given by this, and an arbitrary tensor field here. So the last case, it was very recently solved by Derzynsky, and first of all, he showed the existence of samples in this situation. It was not previously known. And he gave a complete description of all these samples. I will not spend more time here, because this is a very technical construction. But essentially, what you do is that you have, once you have a Osserman metric with these Jacobi operators and non-zero eigenvalue, you may construct local trivializations of the bundle of two forms, which realize the Jordan normal form where you have this kind of isotropy condition on the two forms. And working really is hard work with these two forms. One can show that the kernel of this form psi and the kernel of theta are null distributions. So in this case, you have that your manifold is foliated by two complementary null distributions, but they are not parallel. So in this case, none of these distributions may be a Walker one. And so there is a complete solution to the problem, which depends on some sessions and some connections on some special vector bundles. But I will not spend more time here, just to say that there exists a complete description of all these metrics. So what can we say about the underlying structure of these manifolds? So first of all these Osserman metrics are far to be locally symmetric. Indeed, the only locally symmetric ones are those where the Jacobi operators are diagonalizable, so it corresponds to the real complex and paracomplex space forms. And the other possibility is that the Jacobi operators are two-step nilpotent. In that case, one can construct a family of a rank 2 symmetric space, which is the solution. But that's all. No other Osserman manifold may be locally symmetric. Other properties you have is that, for example, when you take the type 2 Osserman, essentially we have these two families corresponding to two-step nilpotent Jacobi operators, and this one, which corresponds to the case where the eigenvalues are in a ratio 1/4. So all of them are zero curvature homogeneous, and in this case they are curvature homogeneous with a symmetric model. So the curvature tensor is semi-symmetric, but they are not necessarily locally symmetric. And in the second case, all these metrics are indeed symplectic. Indeed, they are almost para-Keller metrics. Even they are more. They are very, very close to the para-complex space forms. They are almost para-Keller metrics of constant para-holomorphization curvature. So they are just so close as close as possible to the para-complex space forms, but they are not. Indeed, as I said, the structure is para-Keller if and only if the connection is flat. And moreover, none of these manifolds can be realized on a compact manifold. So there are examples of type 2 Osserman metrics with nilpotent Jacobi operators on compact manifolds. Indeed, this goes back to some work of Pitian that in the beginning of the 90s that he showed the existence of Einstein self-dual metrics on compact tori, and you can use that work to produce such samples. But you cannot have samples like that for this other case. As concerns the type 3 Osserman metrics, they are even not locally homogeneous, and they also cannot be realized on compact manifolds. I emphasize the fact that they cannot be realized on compact manifolds separately because the techniques are completely different in both cases. In this case, Derdinsky proved the existence of a divergence-free vector field, non-zero vector field, while in this case, we use the fact that you can construct a complex structure on the manifold whose first Chern class is vanishing, and then you get a contradiction. But in all these cases, what we know is that the manifold is a space-like and time-like Jordan Osserman. So as far as up to now, we will only consider the case where we consider information about the eigenvalues of the Jacobi operators. But as you could see, most of the information is not given by the eigenvalues, but also for the Jordan normal forms of the Jacobi operators. So in all the cases, the space-like and time-like Jordan normal form, Jordan Osserman conditions are equivalent, but they are not null Jordan Osserman. Okay. So just a few words about that. Indeed, as I told you when we were at the Lorentzian setting, the space-like, time-like, and null Osserman conditions were equivalent. This is also true in dimension 4. So in this case, space-like and time-like Osserman, this is in black here, this is equivalent in any dimension, and both conditions implied the null Osserman condition. This is also true in any dimension. But the null Osserman condition is also equivalent to a space-like and time-like Osserman, up to our knowledge, only in dimension 4. We were not able to show that for higher dimensions. But when you think on the null Jordan Osserman condition, the non-null Jordan Osserman conditions are equivalent in dimension 4, but the Osserman does not imply Jordan Osserman for the null case. And indeed, the only solution to the Jordan Osserman problem are the space forms of the complex space forms. So this is very much more restrictive than the Osserman case. If we assume that the manifold is Jordan Osserman, indeed here we may only assume it is null Jordan Osserman because this condition implies the other ones. But in this case, Jacobi operators has to be necessarily diagonalizable. And moreover, the case of the para-complex geometry has to be excluded. So this is, as far as we know, the first way to differentiate between the complex and the para-complex geometry just from the properties of the curvature itself, not looking at other things on the manifold. Okay, so I just want to finish, and I would like to say a few things about what you may expect in the higher dimensions. So the situation now is that it's quite close in dimension 4, but what can we say for the higher dimensions? So the first thing, we have to look at the algebraic structure. And here the situation is much more complicated. Indeed, in the dimension greater or equal to 5, the Jordan Osserman conditions for space-like and time-like directions are not equivalent. So this means that at each point on the manifold, even if it is Osserman, you may have directions where the Jacobi operators have some Jordan normal forms and other directions where the Jacobi operators have a different Jordan normal forms. And this makes things really complicated because in this case, there is no hope to express the curvature tensor in terms of a Clifford model structure or something like that, unless you are making some really, really hard compositions there. So on the other hand, if you then assume that the manifold, instead of being Osserman, is Jordan-Osserman, which is a rather more restrictive condition, it was shown by Gilke and Ivanova that in that case, the Jacobi operator has to be diagonalizable in any dimension and in any signature which is non-neutral. So the signature PP, this is a very difficult situation. In that case, you may have other possibilities for the Jacobi operators, but as long as your signature is non-neutral, the Jacobi operator has to be diagonalizable. And unfortunately, the situation is even worse, because if you are in neutral signature, here everything may be the Jacobi operator of an algebraic curvature tensor. So what these results says is that if you take a self-adjoint operator in RLL, you may construct an algebraic curvature tensor where the Jacobi operators are of this form. So it gives exactly A here. The price you have to pay is that you have to increase the dimension to 2p, where p is an 2 to the power L plus 1. And the reason for that, for this high dimension, is that you must ensure the existence of a sufficiently large Clifford model structure. So if you have a large Clifford model structure, then you can play with all these structures, and you can construct algebraic curvature tensors which are Jordan-Osserman and whose Jacobi operator have the properties essentially you want. So there is no much hope to solve the problem at the algebraic level. So, however, what can you say at the differentiable level? Well, first of all, there is a complete classification when the Jacobi operator are diagonalizable with exactly two distinct eigenvalues. So once we know that the Jacobi operators have to be diagonalizable in non-neutral signature, we consider the case, which is the first non-trivial case. If they have only one eigenvalue, then it's a space of constant curvature. So what may happen if you have two different eigenvalues? And in that case, one can give a complete solution. And I will just say that, moreover, you may have Osserman metrics which are non-nilpotent Jacobi operators in any signature, neutral signature PP. Note here, if you look at these Jacobi operators, you have some eigenvalues which are coming from A, but you have a large number of zero eigenvalues. So there was a question whether you may construct Osserman metrics where the eigenvalues of the Jacobi operators are nowhere zero, but they are still Osserman. And this can be done, again, by using this as an application of these modified Riemann extensions. So what you do is, if you take an arbitrary, locally symmetric Ricci-flat pseudo-Riemannian metric, it has to be strictly pseudo-Riemannian. In the Riemannian case, this gives flatness, so it gives no further information. But in the pseudo-Riemannian case, there are many examples where you have locally symmetric Ricci-flat metrics. You take one of these here, and you take the Levi-Civita connection. You construct the associate metric on the cotangent bundle by this expression here. If you this is an Einstein metric on the cotangent bundle, because the extra term you should add here, which is the symmetric part of the Ricci tensor, is vanishing because we are taking Ricci-flat metrics. And one can show that these metrics are Osserman in any signature where the eigenvalues are always 1 to the 4. So this is at this moment the situation of the problem, and well, it seems it will be difficult to say something more about that. So thank you very much for your attention.
Would anybody like to ask a question to our speaker?
Riemannian case, for possible manifolds, you have information about conjugate forms, right? And then there are small results about, if you know the structure of conjugate forms, information about the manifolds. Is used or useful in the Riemannian case?
No, the proof in the Riemannian case were exactly the original proof the way I told you. So what one does is just one firstly solve the problem algebraically. So this gives you a large number of solutions. For example, when you If you remember that those algebraic curvature tensors where you have these Clifford modulo structures, you may construct algebraic solutions for any given number of distinct eigenvalues. So algebraically you have a large number of them, but when you, essentially the question is that then you have to play with the second Bianchi identity. So at the very end of the situation, this is what you are doing. And if you work with that, you can show that the eigenvalues are either one single eigenvalue or two distinct eigenvalues. And in the second case, they are in a ratio 1/4. But there is, well, I don't know if it could be used, for instance, to solve the remaining case of dimension 16, but in the other cases, it was just, the proof was just exactly the way I told you.
Any more questions? Okay, if not, then let's thank our speaker again.
Thank you.